Now, towards the end of my last session, which was our first session on complex numbers, we got familiar with some basic algebra related to complex numbers, some basic geometry related to complex numbers. The Euler representation of complex number z equal to r e power I theta, where r represented the modulus of the complex number and theta the argument of the complex number. Theta, like I mentioned to you in the past, is a multiple valued function, right? If theta is an argument, then theta plus 2k pi will also be an argument. However, of all the values of theta that serve as arguments, one value would lie in the interval minus pi to pi, and that would be referred to as a principal value of the argument, right? And then we examine properties of modulus, properties of argument, properties of conjugate, right? And so on and so forth. Then I told you, while we migrated into the geometry of complex numbers, I mentioned that a complex number z, which is x plus iy, is only a superior substitute for a position vector r, which is like xi cap plus yj cap. X plus iy, a complex number x plus iy, does exactly what a position vector r, xi cap plus yj cap does. It inherits all the properties of the position vector, and in addition has the versatility lot more. While with vectors, you could not perform all arithmetic operations. You could perform, say, addition of vectors, subtraction of vectors, but there was no concept of multiplication or division of vectors or raising one vector to another vector, right? Whereas with z, which is x plus iy, and another z prime, which is x prime plus iy prime, you could perform all acceptable arithmetical operations. That was the merit in migrating from vectors to complex numbers, which is a superior substitute for vectors. Now, if you recall, a quick one at that, if there was a point A with position vector z0. So now, if I talk of a vector z, then, you know, I would keep saying position vector z, position vector z. So I hope, you know, I had got you acclimatized to those conditions where, you know, instead of saying z, I would say position vector z, right? Am I right? So there was a point A with position vector z0, and there was a point B with position vector z. Then this vector would be like a z minus z0, would be like a z minus z0, right? And if this is a line parallel to the x-axis, if this is a line parallel to the x-axis, and if the vector z minus z0 made an angle theta with this line parallel to the x-axis, and this, let's say, is the positive direction of the x-axis, then this theta represented argument of z minus z0. And the length AB was the magnitude of this vector z minus z0, right? So AB was magnitude of z minus z0, and would be some r, say, would be some r. Then this vector essentially had two distinct properties: an argument theta, which is given by this, and a modulus r, which is actually the length of the vector AB, right? And therefore, a suitable Euler representation of z minus z0, an Euler representation of z minus z0 would be z minus z0 equals r e power I theta, where r is the modulus of this complex number z minus z0, and theta is the argument of this complex number z minus z0. Two properties r and theta, modulus and argument, would uniquely set up any complex number or any vector z minus z naught. Now, suppose there was a point A. Say this was a line parallel to the x-axis, and A had position vector z0. This is a quick recap of something that I did earlier, the rotation aspect, but B with position vector z1, this then would be the vector z1 minus z0, right? Say this is a point C with position vector z2. Then this vector AC would be z2 minus z0, right? This angle, say theta 1, would be the argument of z1 minus z0, right? Theta 1 would be the argument of z1 minus z0. Theta 2 would be the argument of z2 minus z0. And the angle between these two vectors, that is theta, the angle between these two vectors, z2 minus z0 and z1 minus z0, theta, would be given by theta 2 minus theta 1, right? Which is like argument of z2 minus z0 minus argument of z1 minus z0. Argument A minus argument B, which is argument A by B, right? So this is like argument of z2 minus z0 divided by z1 minus z0. Now, this geometry you must understand. What this means is argument of this. This is a denominator vector z1 minus z0. This is the numerator vector z2 minus z0. This operation will give me, this operation argument of z2 minus z0 by z1 minus z0 will give me, this operation will give me the angle by which I must rotate the denominator vector so that it coincides with the numerator vector. This operation will give me, this operation argument of z2 minus z0 by z1 minus z0 will give me the angle by which I must rotate the denominator vector z1 minus z0 so that it becomes aligned with the numerator vector z2 minus z0. Yes or no? Which is theta, right? The amount by which z1 minus z0 be rotated so that it coincides with the numerator vector z2 minus z0 is theta, right? Which is what this gives me. So that's the meaning of this operation. That's the meaning of this operation. Argument z2 minus z0 by z1 minus z0. Clear? Now, so now this time to find angle between two vectors, right? It's as simple as this. You're not using dot products or cross product, right? One more thing that you must realize is, if from the denominator to the numerator you have to go anti-clockwise, then theta would be positive. If from the denominator to the numerator you have to go clockwise, then theta would be negative. So it covers practically everything that you require, right? Now, so this is one thing that I had done in an earlier session. Now, say if there is a vector z, this is a certain vector z. This will represent mod z. The angle that this makes with the positive direction of the x-axis will give me argument z, right? And say z is r e power I theta. Z is r e power I theta. That means, say if this is a line parallel to the positive direction of the x-axis, this direction is the positive, and if this angle must be theta, right? The length PQ must be r. PQ represents mod z, and that must be equal to r, and theta represents argument z. This is any vector z, any vector z. This z would be essentially position vector of q minus position vector of p. That means z of q minus z of p. That is what this is going to be. Now, if I multiply this z, this is a vector z, and if I multiply it with e power I phi, I get a vector z prime, say. I get a vector z prime. Z is multiplied with e power I phi. Let's see what happens when I multiply a vector z with e power I phi. With e power I phi. Now when I do that, z is r e power I theta. So this is like r e power I theta plus phi. Yes or no? Right? Yes or no? That means argument of z prime is theta plus phi. Yes or no? Argument of z prime is theta plus phi. Modulus of z prime remains r. Right? Now z prime therefore would be a vector like this, having the same modulus as z, and its argument is going to be theta plus phi. This is going to be the argument of z prime, and this angle therefore is phi. This angle therefore is phi. That means what? If I had a vector z and I multiplied it with e power I phi, the vector rotated by an angle phi. If I had a vector z and I multiplied it with e power I phi, that rotated by an angle phi, that vector rotated by an angle phi to get me another vector z prime. Yes or no? Therefore, such a powerful tool, therefore, realize you could never have imagined this in vectors, but in complex number substitute for vectors, such a thing is so easy to do. That means e power I phi, therefore, is such a convenient operator. Given any vector z, if you want to rotate that vector by phi, you multiply it with e power I phi. So e power I phi is an operator which would rotate any vector z by an angle phi. Multiply any vector z by e power I phi, that vector would rotate by phi. Multiply it with e power I pi by 2, that vector would rotate by 90 degrees anti-clockwise. Multiply it with e power minus I pi by 2, it would rotate by pi by 2 clockwise. Multiply it with e power I pi, it will rotate 180 degrees anti-clockwise, and so on and so forth. Right? So e power I phi is a powerful operator. Multiply any vector with z, multiply any vector z with e power I phi, that vector z would rotate by phi. Clear? Yes, if phi is 2 pi, then z and z prime are aligned. That means that vector is rotated by 2 pi, right? Now, having said all of this, so we had discussed all of this in the past, right? Rotation of vectors. Now, let me get to matters once again. So, I hope this would have reignited complex numbers in you, okay? Now, come to the following equation. Z power n, n is a natural number, n is a natural number, z power n equal to 1. Z power n equal to 1 is a polynomial equation of degree n, right? Z power n minus 1 is a polynomial of degree n. Z power n minus 1 is a polynomial of degree n in z. And this will become 0 for how many values of z? Exactly n values of z, real or complex, distinct or coincident, right? This polynomial will have exactly n roots. N roots, real or complex. That means this will become 0 for exactly n values of z. That means this will become equal to 1 for exactly n values of z, right? So there are n roots to this equation, real or complex, right? The coefficients of this polynomial are real numbers, 1, 0, 0, 0, and then minus 1, right? Coefficient of z power n minus 1 is 0, coefficient of z power n minus 2 is 0, coefficient of z power n minus 3 is 0, coefficient of z power 0 is minus 1, right? They are all real numbers. So, if a plus ib is a root of this equation, then a minus ib will also be a root of this equation. You know what I'm saying? You can also see that straight out of this. If z is a root and z power n equal to 1, let me take the conjugate of both sides. Let me take the conjugate of both sides. Conjugate of 1 will be 1. Conjugate of a real number would be the number itself. Conjugate and n are interchangeable. Conjugate of z power n would be conjugate of z whole to power n. You know why? No. Don't know why, no? See, suppose z is re power I theta. Alright, suppose z is re power I theta. What would z bar be? Z bar is the mirror image of z about the x-axis. If the argument of z is theta, then argument of z bar will be minus theta, right? Z bar will have the same modulus as z, r, but its argument would be minus theta, right? Look at z power n. Z power n is r to power n e power I n theta. That's z power n, right? Z power n, bar of this, bar of z power n. Let me look at bar of z power n, bar of this will be r to power n e power minus I n theta, yes or no? Now, what is z bar to the power n? Z bar whole to power n is going to be r to power n e power minus I n theta. Clear? So, very clearly, z to power n, bar of that is the same as bar of z whole to power n. So, bar and n are swappable, are interchangeable. Clear? Bar and n are interchangeable. Clear? Now, So this clearly justifies. See, if z power n bar is 1, z bar whole to power n is also 1. That means if z satisfies this condition, z bar also satisfies this condition. Yes or no? So z and z bar will always occur in pairs. If z is a root, z bar, its complex conjugate, will also be a root of this polynomial. Clear? Now, let us examine the roots of this. First of all, the roots of this polynomial are customarily referred to as n roots of unity. The roots of this polynomial are customarily referred to as n roots of unity. Any z that satisfies this is called a n root of, it's called a n root of unity. So how many n roots of unity will exist? Exactly n roots of unity will exist, right? Now, this gives me z power n equal to, see, 1 could be written as 0 plus I, 1 plus I into 0, 1 plus I into 0. Which is cos 2k pi, 1 is cos 2k pi, 0 is sin 2k pi. Yes or no? But cos theta plus I sin theta is e power I theta. So far so good? Right? Now, so the various values of z, let's say zk, for any k, a value of z that satisfies this is zk, would be e to power I 2k pi divided by n. That's a root of this. Z is this to power 1 by n. That's a zk. Now, so these zk's are the various n roots of unity. These zk's are the various n roots of unity. To obtain these zk's, the n roots of unity, explicitly, you want to plug in various values of k. Plug in k equal to 0. You get zk equal to 1. That will give you one n root of unity. Plug in k equal to 1. You get another n root of unity, e to power I 2 pi by n. Plug in k equal to 2. You get another n root of unity, e to power I 4 pi by n. Similarly, k equal to 3 up to k equal to n minus 1. So by plugging in k equal to 0, 1, 2, 3 up to n minus 1, you get the various n roots of unity. You get the various n roots of unity. Now, one thing that I want to tell you is, which you can easily see, you would be tempted to ask me this, why would I not plug in more values of k and get more n roots of unity? K equal to 0, 1, 2, 3, n minus 1. And I plug in k equal to n. I get one more n root of unity, k equal to n plus 1. I get another n root of unity. I can keep plugging in various values of k and get various n roots of unity. The truth of the story is, I have taken these n consecutive values of k. Now, if you plug in k equal to 1, you get the same value of this as k equal to 0. See, for example, k equal to 0 gives me z0, for example, as 1. Similarly, look at a k after this, which is k equal to n. K equal to n, zn, say, would be e power I 2 pi, which is cos 2 pi plus I sin 2 pi. Which is 1. So see, k equal to 0 and k equal to n are giving me the same value of z. Similarly, I claim that k equal to 1 and k equal to n plus 1 will give me the same value of z. K equal to, so the same set of values will get replicated. If I take another n consecutive values of k, then the same set of values of zk will get replicated. You can check. Yes. Huh? Yes. Please go. Take the rear door. So, so from k equal to 0 to n minus 1, you're taking n consecutive values of k and getting the various n roots of unity. Or you could have also started from k equal to n and taken n consecutive values of k, and you would have got the same set of n roots of unity replicated. Or you could have started from k equal to 1 and gone all the way to n. You would have got the same set of n roots of unity but shuffled in a different order. Essentially, the rule of the game is any n consecutive values of k could be taken. You can start with any value of k and drive through n consecutive values of k and get the various n roots of unity depending on the starting point of k that you have chosen. The various n roots of unity would appear in various orders. That's all. It'll get shuffled. But the same set will essentially appear if you take a string of length n. Any n consecutive values of k would suffice. So it's customary to take 0 to n minus 1, right? Now, I mean, you could have started with k equal to minus 1 and gone all the way to n minus 2. That's also okay, right? Now, see, n could be even, n could be odd, right? Say n is even. Then there will be two real roots of this, plus 1 and minus 1. Two real roots plus 1 and minus 1. And n minus 2 complex roots. Now, if n is even, n minus 2 would be even. Total number of complex roots come in pairs, so you would have only even number of complex roots. So n minus 2 is even, which is a consistent fact to obtain, right? Similarly, if n is odd, then the only real root of this would be z equal to 1. The only real root would be z equal to 1. The remaining n minus 1 roots would be complex. Now, if n is odd, n minus 1 will be even, an even number of complex roots. Why? Because they come paired. Number z and z bar both would be roots. If z is a complex root of this equation, then z bar will also be a complex root of this equation, right? And this z and z bar will appear for different values of k, will appear for different values of k, right? Now, also notice that no matter what, this polynomial equation z power n minus 1 equal to 0, z power n minus 1 equal to 0 could be written as z power n plus 0 into z power n minus 1 plus 0 into z power n minus 2. Going this way, minus 1 equal to 0. What are the roots of this? These zk's. z0, z1, z2, zn minus 1 are the roots. Now, sum of all roots of this polynomial would be minus the coefficient of the second highest power divided by the coefficient of the highest power, right? Which means sum of all zk's, sum of all the n roots of unity, k equal to 0 to n minus 1, sum of all the n roots of unity will always be 0, minus of 0 divided by 1. That's going to be sum of all the n roots of unity, right? Clear? Now, all's good? Notice also the following. See, if I say there is a complex number z such that mod z is 1, what does it mean? What does mod z mean? Distance of z from the origin. If I say mod z is 1, that means z is a complex number whose distance from the origin is 1. That means z lies on a circle centered at the origin and radius 1. This is what it means. That means mod z equal to 1 would mean, if this is the origin O, this is a circle centered at O and radius 1, then z could be any point on this circle. The position vector z could be any point on this circle. Mod z equal to 1 represents various complex numbers z lying on a unit circle centered at the origin. Unit circle centered at the origin. If I said mod z minus z naught equal to r, what does this mean? Z naught is a fixed complex number. Z naught is a fixed complex number. Z is a moving complex number. It means z, a moving complex number, is such that its distance from z naught is always r. That means z lies on a circle centered at z naught and radius r, right? So in this case, z lies, mod z minus z naught equal to r represents a circle whose center has position vector z naught, whose radius is r. Then z could be any point on this circle, mod z minus z naught equal to r. This represents a circle centered at z naught and radius r. Right? Now, having said this, come down to these zk's. Come down to these zk's. These zk's are the various n roots of unity, right? And also realize that if I took mod of e power I theta, it's like mod of cos theta plus I sin theta, which is root cos square theta plus sin square theta. Which is 1? Yes or no? Therefore, mod of e power I theta, if theta is a real number, will always be 1. Will always be 1. Yes or no? So then, if I took mod of zk would be mod of e power I 2k pi by n, mod of e power I theta, and this is going to be 1. Theta is real, theta is 2k pi by n, so this is going to be 1, right? So mod zk turns out to be 1. Mod zk turns out to be 1, which means what? Zk lies on a unit circle centered at the origin. Yes or no? That means if I have a circle centered at the origin and of radius 1, then for any k, these various zk's would get positioned on this circle. Right? For different values of k, these zk's will have different positions, but they would all lie on the circle whose center is 0, the origin, and whose radius is 1. Right? So all the n roots of unity lie on a unit circle centered at the origin. On a unit circle centered at the origin. Right? Yeah, but then here n will not tend to infinity, because if I am talking of a polynomial of degree n, then I am not talking of a polynomial of degree infinity. Yeah, more points on the circle, they will be more densely populated on the circumference. Yes, you are right. Absolutely. They will be more and more densely populated on the circle. Now, see, so this is a unit circle centered at the origin. This zk for various values of k 0 to n minus 1 constitutes a sequence zk. Constitutes a sequence zk. There is a sequence zk constituted here. Clear? K equal to 0, z0, z1, z2, zn minus 1 is a sequence. Now, if I take two consecutive values of k, then I get consecutive members of the sequence. Then I get consecutive members of the sequence. Now, if zk is this for a certain k, then the member just before this is going to be zk minus 1. Right? That's going to be e power I to k minus 1 into pi by n. Right? Yes or no? Which means zk by zk minus 1. If I divide this by this, then I get e power I 2 pi by n, which is independent of k. Yes or no? Do you realize? If I divide this by this, I get e power I 2 pi by n, which is independent of k, which is a constant independent of k, which is a constant independent of k. That means z1 by z0, z1 by z0 must be the same as z2 by z1, must be the same as z3 by z2, must be the same as z4 by z3. Therefore, these zk's must constitute a geometric progression. These zk's, the various n roots of unity, are in GP, whose common ratio is e power I 2 pi by n. Yes or no? So these zk's constitute a geometric progression with common ratio e power I 2 pi by n. Common ratio e power I 2 pi by n. Right? So not only are these zk's located geometrically on a unit circle centered at the origin, these zk's are also in GP with common ratio e power I 2 pi by n. So far so good, right? Now, zk by zk minus 1 is a complex number which is e power I 2 pi by n. What's the modulus of this complex number? 1. What's the argument of this complex number? 2 pi by n. Right? Which means argument of zk, two consecutive k's, that is zk minus 1 is 2 pi by n. Right? That means, say, zk minus 1 is located somewhere here. Zk minus 1 is located somewhere here on this unit circle. And zk is located somewhere here. Right? Now what does this mean? This means zk minus 1 is what? Zk minus 1 minus 0. Zk is what? Zk minus 0. Zk minus 0, the numerator vector is this vector. Zk position vector of this, zk minus position vector of this, which is 0. Zk is this vector, zk minus 0. The denominator vector, zk minus 1 minus 0 is this vector. Right? Now what does this mean? The amount by which you must rotate the denominator vector so that it coincides with the numerator vector is 2 pi by n. That means this angle is 2 pi by n. Similarly, if I took zk plus 1, if this was zk plus 1, the next value of k, then this angle will also be 2 pi by n. If I took zk plus 2, which is the next zk, then this would be 2 pi by n, yes or no? Now, notice then that these zk's have equal angular spacing on the circle. These zk's have consecutive zk's. Consecutive zk's have equal angular spacing on the circle. Yes or no? If such be the case, this is k equal to 0, z0, then you will have z1, k equal to 1, z2, zn minus 1, right? This is the origin O. All these angles are 2 pi by n. See, this angle will be 2 pi by n. This angle will be 2 pi by n. This angle would be 2 pi by n. These are the various locations of these zk's, right? Now, if these angles are equal, then do you realize that these chords would be equal? Equal chords subtend equal angles at the center? Yes or no? Yes or no? This chord would be the same as this chord, would be the same as this chord, and so on and so forth. That means these zk's constitute the vertices of a regular n-gon polygon. Yes or no? These zk's constitute the vertices of a regular n-gon polygon. They are vertices of a n-gon polygon because they are n in number. But now you can see that z0, z1, z2, zn are vertices of a regular n-gon polygon. The n roots of unity lie at the vertices of a regular n-gon polygon. Right? Huh? They are in? What are in AP? ZKs are in AP? No, they are not. They are in GP. ZK minus 1 is not the same as ZK minus 1 minus ZK minus 2. No. These ZKs are in GP. They are not in AP. These ZKs are in GP only. They are not in AP. Ratio of these ZKs is independent of K. But the difference of these ZKs is not independent of K. I can establish that if you want. Zk is like this. Zk minus 1, take K minus 1. Take a difference. You will not find it independent of K. So Zk's are not in AP. Zk's are in GP. Right? So Z0, Z1, Z2, etc. constitute the vertices of a regular n-gon polygon. Clear? Now, in fact, the way they would be spaced out on the circle, suppose n is even, the circle on which the various n roots of unity lie in the Argand plane? Suppose n is even. Then there will be two real roots. Z equal to plus 1 is here and z equal to minus 1. Z equal to plus 1 will be a root and z equal to minus 1 will be a root. Right? Two real roots. This is 1 plus I into 0. This is minus 1 plus I into 0. Two real roots, plus 1 and minus 1. And the rest, n minus 2, would be complex roots. So then what would happen is, n minus 2 complex roots, half of them would be on the upper half of the circle, half of them would be on the lower half of the circle. That means on the upper half of the circle, you will find n minus 2 by 2 roots, and on the lower half of the circle, you will find n minus 2 by 2 roots. Yes or no? Right? Yes or no? In fact, if there is a certain zk, which is a root lying on the upper half, then there is going to be a zk bar, which will lie as a mirror image of zk on the lower half. The number and its conjugate, would lie on different semicircles. One would lie on the upper half, the other would lie on the lower half of the circle. Clear? And of course, this will be zk for some other value of k. This would be zk for some other value of k. Now, similarly, if n is odd, there will be only one real root, z equal to 1. Only one real root, 1 plus I into 0, right? And there would be n minus 1 complex roots, right? Then n minus 1 complex roots, half of them will lie on the upper half of the circle, n minus 1 by 2, and half of them would lie on the lower half of the circle. Yes or no? In fact, if n is odd, I could have said the following. One way or the other, n even or odd, sum of all the n roots of unity will be 0. Sum of all the n roots of unity would be 0. Say if n is odd. Then, first of all, this first expression, true whether n is even or odd. Sum of all the n roots, k equal to 0 to n minus 1, will always be 0. So, let me examine when n is odd. Now, when n is odd, the only real root would be obtained for k equal to 0, that is z equal to 1, right? Let me isolate k equal to 0. So, that becomes z0, which is 1. From this summation, let me strip z0 out of this summation. Then I have the remaining zk's. This time, k equal to 0 is included here, so this will start from k equal to 1 to n minus 1. Right, what I could do is, I could take k equal to 1 to n minus 1 by 2 as all the roots lying on the upper half, right? All of this must add up to 0. One plus summation. What I do is, in this summation, I take k equal to 1 to n minus 1 by 2, half of the complex roots. K equal to 1 to n minus 1 by 2. All the zk's. And with every such zk for these complex roots lying on the upper half, I take a zk bar starting from k equal to 1 to n minus 1 by 2, I've included all the zk's and I've included all the roots lying on the lower half by taking zk bars? Yes or no? You know what I'm saying? So zk plus zk bar, 1 plus summation zk plus zk bar will be 0 this time. See, I hope you realize the zk bars, the moment I take zk bars, then for every k lying on the upper half, I've taken a zk bar which lies in the lower half. So I've actually covered all the zk's. By just taking roots in the upper half of the circle, I have covered all the zk's. By taking these zk bars, I have covered these zk's lying on the lower half of the circle. Yes or no? Clear? So this will be 0 then. Now zk plus zk bar is what? Zk plus zk bar is twice real zk. See, isn't it? If you take a complex number z and add it to its conjugate, then it's going to be twice real part of z. It's going to be twice real part of z. So this is going to be twice real part of zk, right? It's going to be twice real part of zk. Clear? So this would be 1 plus twice real part of zk, k equal to 1 to n minus 1 by 2. That must be 0. Yes or no? Right? Now, see, there is a result which so far so good, right? Now, suppose I took something like this. Say n odd means say n is of the form 2n plus 1. 2n plus 1 roots of unity, this will give me 2n plus 1 roots of unity, right? Where in this case the zk's would be e to power I 2k pi divided by, instead of n you have 2n plus 1, where k takes up values like 0, 1, 2 up to 2n. Yes or no? These are 2n plus 1 consecutive values of k. These are 2n, right? This will have 2n plus 1 roots. So I'll have to take 2n plus 1 consecutive values of k. 0 to 2n will give me the 2n plus 1 roots of unity, right? Right? The only real root would be for k equal to 0, which will give me z0, which is 1. Right? 1 to 2n, I'll have all complex roots. 1 to 2n, I'll have all complex roots of unity here. Now, again, sum of all the zk's, k runs from 0 to 2n, will be 0. Sum of all complex roots will always be 0 for unity, right? I isolate k equal to 0. So if I isolate k equal to 0, I get 1, z0, and then the rest I write as summation zk, k equal to 1 to 2n. 2n roots of unity, 2n complex roots of unity, 2n complex roots of unity, 1 real root of unity in this. That's equal to 0. Right? Now, from k equal to 1 to n, I'll get roots on the upper half of the circle. Then n plus 1 to 2n, I'll get roots on the lower half. And roots in the lower half of the circle are only conjugate of roots on the upper half. So what I could do is, I could conveniently write this as 1 plus summation. I take only the upper half of the circle, 1 to n. And I take all the zk's. To include points in the lower half of the circle, I take a zk bar. That must be 0. Yes or no? By taking a zk bar, I can avoid taking values of k n onwards. K equal to 1 to n will give me all the zk's. K equal to n plus 1 to 2n will give me all the zk bars. So I just take k equal to 1 to n and I include the zk bars right here. Right? Which then means zk plus zk bar is twice real zk. Is 0 summation sorry, let me just rewrite this. 1 plus twice summation k equal to 1 to n real zk equal to 0. This brings us to a very important result in trigonometry. So that's the reason I'm spending so much time on this. So this gives me 1 plus, now zk is this. What is zk? Cos 2k pi by 2n plus 1 plus I sine 2k pi by 2n plus 1, right? That's zk e power I theta cos theta plus I sine theta. What's real zk? Cos 2k pi by 2n plus 1. Cos 2k pi by 2n plus 1. K equal to 1 to n must be 0. That means cos summation cos 2k pi by 2n plus 1 k equal to 1 to n must be minus half, right? Go back to your dusty trigonometric books and you would find the first chapter in trigonometry where they'll say prove cos 2 pi by 2n plus 1 plus cos 4 pi by 2n plus 1 plus cos 6 pi by 2n plus 1 cos 2n pi by 2n plus 1 equal to minus half. You'll find problems where they could take various values of n, they could ask you to prove similar results, right? So this summation cos 2k pi by 2n plus 1 equal to minus half is so conveniently obtained using n roots of unity. With trigonometry it would have been more work, more effort, right? So remember this as a standard result, right? And the technique that we have deployed to establish this could be used at various other places. Right, now, all's good so far, right? It will be, na? See? It will be. I mean, summation and real are interchangeable. You want me to prove that? No? Now, see, z power n minus 1. right? It has n roots. The n roots of unity. Say, let me just change notation for a few minutes. Say alpha 0 would be for k equal to 0, that is like z0. Then alpha 1 would be another root for k equal to 1. z1, that is alpha 2 would be z2. Alpha n minus 1 would be zn minus 1. These are the various n roots of unity. z0, z1, z2. This time I am calling them alpha 0, alpha 1, alpha 2, alpha n minus 1. All right. Now, this has these as its roots. That means if I have to factorize this polynomial, then z minus alpha naught would be a factor, where alpha naught is 1. Alpha naught is 1, right? Z minus alpha 1 will be a factor. Z minus alpha 2 would be a factor of this. Z minus alpha n minus 1 would be a factor of this. Where what are these? These are the n roots of unity, right? So this could be factored into z minus 1, which is alpha naught, into z minus alpha 1 into z minus alpha 2 into z minus alpha n minus 1, right? These are the factors of z power n minus 1. Is this an equation or an identity? It's an identity. It's true for all values of c. Whenever you factorize, you don't get an equation, you get an identity, right? Now, I also claim that z power n minus 1 could be factored as z minus 1. Another way to factorize this is z minus 1 into 1 plus z squared plus z power n minus 1. Why so? Yes, realize that sum of this GP series is this divided by this, isn't it? Right? So this is also an identity? Yes or no? This expression is identical to this. This expression is identical to this. So these two expressions are identical to each other. Right? These two expressions are identical. Right? Together they constitute an identity. Now z minus 1 is identical to this. That means this must be identical to this. Right? Which means that z minus alpha 1, z minus alpha 2, z minus alpha 3, z minus alpha n minus 1 is identical to 1 plus z squared plus z power n minus 1. This is this identity and therefore true for all values of z. I can plug in z equal to alpha, beta, gamma, root 2, 1 mole, 50 moles, Avogadro's number, or also z equal to 1. Right? Let me plug in z equal to 1 on both sides. Right? I get 1 minus alpha 1 into 1 minus alpha 2 into 1 minus alpha n minus 1 equal to 1 plus 1 plus 1 plus 1 n times. That makes it n. This is a special property of n roots of unity. This is a special property of n roots of unity. where these n roots of unity exclude z equal to 1. Alpha 1, alpha 2, alpha n minus 1 exclude z equal to 1, right? Because that was alpha 0 I have excluded. So these are n roots of unity to the exclusion of alpha 0, which is 1. Clear? Now, this is a mighty useful property. See what all it gives us. Can I wipe this off? Realize that the alpha k's are like zk's, which is like e power I 2k pi by n. E to power I 2k pi by n. These are my alpha k's. These are my alpha k's. K equal to 1 to n minus 1 will give me alpha 1, alpha 2, alpha n minus 1. Right? So this property of these n roots of unity, 1 minus alpha 1 into 1 minus alpha 2, 1 minus alpha 3 into 1 minus alpha n minus 1 equal to n. Let's see what it gives us. See, let me look at any one of these factors, say 1 minus alpha k. These are factors of the form 1 minus alpha k, k equal to 1 to n, right? The whole thing is product of terms of this kind, k equal to 1 to n minus 1, right? 1 minus alpha k is like 1 minus e to power I 2k pi by n, right? Yes or no? Which is like e power I k pi by n if I take common, then inside the parenthesis e power minus I k pi by n minus e power I k pi by n. This is what it gives me. Yes or no? Yes or no? Which is of the form e power minus I theta minus e power I theta. E power minus I theta minus e power I theta. Yes or no? Hey, e power minus I theta is cos minus theta, which is cos theta minus I sin theta. Sin minus theta is minus sin theta. And e power I theta is like a cos theta plus I sin theta. Right? So if I take this difference, then e power minus I theta minus e power I theta is going to be minus 2I sin theta. Is going to be minus 2I sin theta. Yes or no? Right? Which means this expression reduces to e power I k pi by n minus 2I sin k pi by n. Yes or no? K equal to 1 to n will give me various members here. If I took the modulus of minus I, I'll get 1. If took the modulus of e power I k pi by n, I'll get 1. Yes or no? Now, k runs from 1 to n minus 1. So k by n will be less than 1. K runs from 1 to n minus 1. Since k is less than n, k by n will be less than 1. So this will be less than pi. So sin theta, if theta is less than pi and greater than 0, will be positive. So if I took the modulus of this, then it will be sine k pi by n only, because this is a positive number. Right? Now, look at this product. This product is represented by pi. K equal to 1 to n. Terms of this kind, right? Minus 2i e power I k pi by n sine k pi by n, k equal to 1 to n, equals n, yes or no? See, these are all 1 minus alpha k's, product of terms of the kind. These are all 1 minus alpha k. See, 1 minus alpha k precipitated as this term, which is this. Product of terms of this kind, k equal to 1 to n. Right? Equal to n, yes or no? Are you confused? No? Can I remove the clutter from you? Now, let me take the modulus of both sides. N is a natural number. This will give me 2. And this 2 will appear n times, right? K equal to 1 to n. This 2 will appear n times. So this will become 2 to the power n. Right? Minus I modulus would be 1 for all the terms. So 1 into 1 into 1 n times. Right? That will be 1. Each of these e power I k pi by n. For any k would be 1. Mod of this would be 1. So 1 into 1 into 1 n times. That will be 1. And these would be, for k equal to 1, for example, you will have sine pi by n. For k equal to 2, sine 2 pi by n. K equal to 3, sine 3 pi by n. K equal to n minus 1, sine n minus 1 pi by n equal to n. Yes or no? This is what you get. And modulus of these sines is the sine itself, because all these sines, you know, these angles are less than pi. Because the highest angle itself is less than pi, see? K n minus 1, sorry, k n minus 1. Yeah, k runs from 1 to n minus 1. I'm so sorry about that. So this would be 2 to the power n minus 1. This should be 2 to the power n minus 1, because they would be n minus 1 2s. They would be n minus 1 2s. Right? N minus 1 factors in this. So 2 to the power n minus 1, sine pi by n, sine 2 pi by n, sine 3 pi by n, sine n minus 1 pi by n is n. Yes or no? This gives me the product P, which is sine pi by n into sine 2 pi by n into sine n minus 1 pi by n equals n by 2 to the power n minus 1. N by 2 to the power n minus 1. Again, go back to your dusty trigonometry books. They'll very often say, find the value of sine pi by 3, or say pi by 11, 2 pi by 11, 3 pi by 11 into sine 10 pi by 11. And you'll equals, let's say, 11 by 2 to the power 10. Right? Try doing this with trigonometry alone. It'll be nothing less than getting bamboozled. But now we have such a crisp, elegant way of looking at it from the perspective of complex numbers, and roots of unity offer to us so much more. I will repeat all steps. Did you understand this? After this, see, how many factors are of this kind are there in this product? N minus 1 factors, right? What I'm doing is, this is an equation, I take modulus of both sides. Modulus of n will be n itself. Now, modulus of minus I will appear n times. So I take the modulus of minus I into modulus of minus I into modulus of minus I into modulus of minus I n minus 1 times. Each of these modulus of minus i's would be 1. So 1 into 1 into 1 n minus 1 times. Now, then there is e power I pi by n into e power I 2 pi by n into e power I 3 pi by n. I take the modulus of each of these. Modulus of the product would be product of the moduli. So modulus of each of these e power I pi by n would be 1, e power I 2 pi by n would be 1, e power I n minus, and modulus of these signs would be 1, would be the sign itself. Why? Because k is less than n. K equal to 1 to n minus 1 means k is less than n. That means this angle lies in the first and the second quadrant, in which sign is positive, so modulus of sign would be the sign itself. So that's why these signs just get automatically multiplied out. Sin pi by n, modulus of sin pi by n would be sin pi by n. Modulus sin 2 pi by n would be sin 2 pi by n, and so on and so forth. And modulus of n would be n. N is a natural number anyways. Right? So which brings us to this very, very useful result in trigonometry. Right? This result and the earlier result in trigonometry can come in very handy to you. Remember these results and see how we've got. Now you don't have to, otherwise what you would have had to do is, in order to establish this result, you would have to, No, that'll not work here. That'll not. I'll have to convert all the products into sums and manipulate like mad, monstrous. If it was all sines, if it was all cosines, then it would have been multiplying by cosine of the smallest angle and catalyze the whole process. But if it is sines, then there is no catalyst. See, if it was cos theta into cos 2 theta into cos 2 square theta into cos 2 cube theta into cos 2 to power, then multiplying numerator denominator with sin theta will work. But if it was product of sines, then that's not going to work. It's going to be horrendous dealing with this, with that. Got me? So far so good, right? Now, if I had z cubed equal to 1, it'll give me the 3 cube roots of unity. It'll give me the 3 cube roots of unity. The roots of this would be zk. N is 3 in this case. N is 3 in this case. The 3 cube roots of unity would be e power I. N is 3. So 2k pi by 3, where k could be given values like 0, 1 and 2, or any 3 consecutive values of k. Once again, these 3 cube roots of unity, like before, will lie on a unit circle centered at the origin. These zk's would be in geometric progression with common ratio e to power I 2 pi by 3. And they constitute the vertices of a regular three-gon polygon. A regular three-gon polygon is an equilateral triangle. So the 3 cube roots of unity lie on a unit circle centered at the origin, constituting vertices of an equilateral triangle. Right? So which means the 3 cube roots of unity, z0 for example is 1, k equal to 0, z0 is 1 of the cube roots of unity, right? And do you realize that the angular separation between the various zk's is 2 pi by 3? In the earlier case it was 2 pi by n, in this case the angular separation is 2 pi by 3. So if z0 is located here, this is the origin, then z1, which is e power I 2 pi by 3, is located here, and this angle is 120 degrees. Yes or no? And z2 is k equal to 2, means e power I 4 pi by 3. That means another 2 pi by 3 from here. Right? The angular separation between z1 and z2 will also be 2 pi by 3. Yes or no? Where ABC will constitute vertices of an equilateral triangle. This is Z2. This is Z2. Z2, which is e power I 4 pi by 3? Yes or no? Where this ABC is an equilateral triangle. If A is the origin, then these angles are all 120 degrees. 120 degrees. 120 degrees. Now, notice that as far as Z2 is concerned, this is 4 pi by 3. 2 pi by 3 plus 2 pi by 3. So, this angle is also 2 pi by 3, but in a clockwise sense. So, this is like minus 2 pi by 3. Right? So, an argument which is 4 pi by 3 is the same as an argument which is minus 2 pi by 3. So, this could also be written as e power minus I 2 pi by 3. Because 4 pi by 3 is the same as minus 2 pi by 3. Right? Anti-clockwise. This is clockwise and this is anti-clockwise. Right? So, argument of Z2, which is 4 pi by 3, is synonymous with a clockwise rotation of minus 2 pi by 3. So, argument could also be read as minus 2 pi by 3. And do you realize that Z1 is e power I 2 pi by 3, Z2 is e power minus I 2 pi by 3, and they are conjugates of each other? E power I theta and e power minus I theta would be conjugates of each other, which is what you expected. Z1 and Z1 would be Z2 bar, Z2 would be Z1 bar. They are mirror images of each other about the real axis, that is the x-axis. Right? Now, so this is a root 1. If I choose to call this Z1 as omega, the other cube root of unity, then Z2, do you realize, is also Z1 squared? See, e power I 4 pi by 3 is the square of Z1. Is the square of Z1. So this is Z2, which is omega squared, where omega is looked upon as e power, omega is looked upon as e power I 2 pi by 3. Right? So, the three cube roots of unity are 1 omega and omega squared. And this 1 omega omega squared lie on a unit circle centered at the origin with a mutual angular separation of 2 pi by 3, constitute the vertices of an equilateral triangle. Omega and omega squares are conjugates of each other. Right? And sum of all the n roots of unity is 0. So 1 plus omega squared must be 0, because sum of all the n roots of unity is 0. Right? So which means 1 plus omega squared must be 0. Right? So sum of all the n roots of unity, this time cube roots of unity, will be 0. Clear? Where omega and omega squared, I repeat, are conjugates of each other. If this is e power I 2 pi by 3, this is e power I 4 pi by 3, which is the same as e power minus I 2 pi by 3. Right? Not only that, this cube root of unity is the square of this. This cube root of unity is the square of this. Now if I square omega, then this becomes omega to power 4, which is omega cubed into omega. Hey, but omega is a root of this. So omega cube must be 1. Since omega is a cube root of unity, omega satisfies this equation. 1 omega and omega squared are essentially roots of this. So omega satisfies this equation. So omega cube must be 1. So omega cubed is 1, which gives me omega. That means this is the square of this, and this is also the square of this. So the two complex cube roots of unity are squares of each other, That you would not find in real numbers. But in complex numbers, such a beautiful thing occurs, right? Omega and omega squared. Omega square is the square of omega, and the square of omega squared will give me omega. They are squares of each other. This is one cube root of unity. Square this. This would be omega to power 4. which would be omega cubed into omega. But omega cubed is 1. Because omega and omega squared both satisfy this. 1 omega omega squared are roots of this equation only fundamentally. So if you plug in z equal to omega, omega cubed is 1. So this becomes 1. This becomes omega. That means the square of this is this. And the square of this is this. They are squares of each other. Diptesh. Got me? No. I never assumed that there isn't an alpha I there which is not minus 1. There could have been an alpha I which is minus 1. When did I assume there is no alpha I which is not minus 1? Right? Assume that. Right? And you know, some people will just create unnecessary identities out of z power n minus 1 equal to z minus 1 into z minus alpha 1 into z. I mean, I plugged in z equal to 1. To that extent, it's all right. Some people will also plug in z equal to minus 1, will create another result out of it and say, bingo, that's my result. Z equal to minus 3 and another result. Z equal to 2, another result. Just because it's an identity, use it the way you like unnecessarily. That's wasteful. Right? Z equal to 1 is a useful result. It has implications. But other things, you know, you don't have to mug up identities related to 50,000 Z's. Right? So, now, all's good so far, right? Now there are some factorizations that could be done with the help of this cube root of unity. See, for example, if you had like x squared plus x plus 1, an expression like a x square plus x plus 1, realize that 1 plus omega plus omega squared is 0. These are the three cube roots of unity. Omega is e power I 2 pi by 3. Omega squared is e power I 4 pi by 3, which is the same as e power minus I 2 pi by 3. Now this expression will have no real factors, but it can have complex factors. See, I could write this as x squared minus omega plus omega squared into x plus omega cubed. I could write it like this. 1 could be written as omega cube. Yes or no? Now I take these two, right? And I get x into x minus omega. And I take these two minus omega squared into x minus omega, right? Which then turns out to be x minus omega into x minus omega squared. Right? Yes or no? Which means if I had, say, x cube minus 1 as an expression, I could have written this expression as x minus 1 into x squared plus x plus 1. Which is like x minus 1 into x minus omega into x minus omega squared. Yes. Right? Similarly, x cubed plus 1 could have been written as, okay, come to the general form. If in this expression, I replace x by a by b. X by a by b. Then a cube by b cube minus 1. So which is like a cube minus b cube by b cubed, etc. And this would be a by b minus 1, etc. Then what you would end up getting is a cubed minus b cubed as a minus b, a minus omega b into a minus omega squared b is what you'll get. If you plug in x equal to a by b, then this is what you'll get. This is what you'll get. This is an identity. Replace b by minus b. Replace b by minus b in this case. So this will become minus b whole cube. So a cube plus b cubed is what it would become. Which is a plus b, a plus omega b into a plus omega squared b. Right? These are two important identities written in terms of omega and omega squared. Right? Another important identity is exactly the same way, but I'll just tell you the final result. This expression could be factorized as whose was that? Switch it off. This could be factorized like this: a square plus b square plus c squared minus ab minus bc minus ca has these as its factors: a plus b omega plus c omega squared into a plus b omega squared plus c omega. Given this, do you all know how to factorize a cube plus b cube plus c cube minus 3abc? This is like a plus b plus c into plus b squared plus c squared minus ab minus bc minus ca, right? Which is a plus b plus c into a plus b omega plus c omega squared this is another identity which is often used, right? Must remember all these identities. Now, see, I still can't forget our teacher in Bella High, R.C. Pathak, our maths teacher, who in class 7 asked us to factorize x power 5 plus x power 4 plus 1, when other people were just about beginning to learn to factorize a squared minus b squared. Now at this point of time, I find it very easy to deal with it, because you know, if you plug in x equal to omega, this will become 0. See, 0 means this would be like omega cubed into omega squared. This will become omega cubed into omega, which would be omega plus 1, which would be like omega squared plus omega plus 1. That means omega is a root of this. So omega squared must also be a root of this. Then I know for sure that both omega and omega squared are factors of this. Both are factors of this. That means I know that this actually reduces to x squared plus x plus 1. So I now know very readily from complex numbers that this is a factor of this. But at that point of time in class 7, it was brute force algebraic manipulation that we had to take recourse to, right? Neither did we know remainder theorem, nor did we know complex numbers, but ab initio from first principles, we had to work around this. And it was a lot of work, lot of challenge. All of class 7, the entire bunch of 35 students in my section got 0. We used to have what they referred to as monthly tests. So he would say, this gentleman would say, okay, whatever marks you get, I'll multiply by 30, the monthly test. So it didn't make a difference. We still got the same marks. So you understand how much we got in each of the monthly tests, the entire batch. And it's the same batch of some 30 plus students, out of which, some 20 students took science, the rest took commerce. And out of these 20 students, 15 or 16 went to IIT, with 2 people getting All India rank 20, 1 person getting a rank of 23rd, 1 in 30s, 146. He used to be known as Chacha, because even when in class 7, he used to look so elderly. So we used to call him Chacha when he was still a kid. 1 Debashish 60, 190, 60s, 90s, 176, and so on and so forth. This was the set of ranks from that 15 students. Everyone getting zeros in the monthly tests of R.C. Pathak. But I'll tell you, these large part of our ranks we owe to this gentleman, because he got us into a state where, it didn't intimidate us taking to new things in an exam, even if kids normally, work out problems from their textbook, and the same problems with numbers changed is what they give in the exam. But this gentleman got us acclimatized to this thought of, thinking independently, and even if it's a new situation, work around it. We failed to solve his problems in the exam, but we learned how to deal with it sooner or later. So a lot of credit goes to, if such a person were to be teaching in a school now, and the entire class got zeros, there would be a herd of parents coming down with banners, protests, and court cases. But in our case, we knew that if we went and complained at home, instead we would get hit at home. So you'd rather not say we were happy getting those zeros, but people in our parents realized that this gentleman must be doing the right job, since everyone got zeros. And some parents who were not educated didn't anyways bother about marks when we were kids. Those who were educated analyzed it from a very rational perspective, and they always thought whatever the teacher did was right. And that helped everyone. And I still know, despite the fact that he was such a great teacher, he was very absent-minded. So he would come to the class wearing a green pant, leave the class wearing a blue pant, because we would carry fountain pens with blue ink, and while he would solve problems on the board, we would make his green pant blue. All right, so then no, it's one factor I know. Now I can manipulate. So I could write x power 5 as some x cubed into x squared plus x plus 1 and adjust terms and factorize. If I know one factor, then I can factorize it. I'm not saying this is the factorization. These are two factors. There would be one more factor. Oh, okay. Now, if there is an equilateral triangle, vertices have position vectors z1, z2, z3. Right? These are the position vectors of the vertices z1, z2, z3. The result for an equilateral triangle is 1 by z1 minus z2 plus 1 by z2 minus z3, 1 by z3 minus z1 must be 0. If z1, z2, z3 are the vertices of an equilateral triangle, then summation 1 by z1 minus z2 must be 0. Let's establish this result. It's a regular result. Let's take a plunge into this result. Okay, how to prove this result? I'll just create some room here. All these angles are 60 degrees. I want to show that this expression must be 0 if this triangle is equilateral. All right. Let me look at this expression. Let me take from this expression 1 by z1 minus z2 common. From this expression on the left hand side, let me take 1 by z1 minus z2 common. Then this becomes like a 1 plus z1 minus z2 divided by z2 minus z3 plus z1 minus z2 divided by z3 minus z1. Let me look at this. We want to show that this is 0. Now, let me look at this vector, for example, z1 minus z2 by z2 minus z3. z1 minus z2 by z2 minus z3. This vector would have a modulus r and would have an argument theta. Would have a modulus r would be mod of this, theta would be argument of this. Yes or no? Right? What is r? R is the modulus of this complex number, which is mod of z1 minus z2 divided by z2 minus z3. Right? Modulus of the ratio would be ratio of the moduli. Modulus of the ratio would be ratio of the moduli. So this is mod of z1 minus z2 divided by mod of z2 minus z3. Now, mod of z1 minus z2 is the distance between z1 and z2, which is the side AB. Mod of z2 minus z3 is the distance between z2 and z3, which is the side BC, which is 1. Yes or no? Because AB equal to BC equal to AC in an equilateral triangle. So the modulus of this complex number is 1. So R will be 1. R turns out to be 1. Let me find the argument of this complex number, theta, right? Now, theta is argument of z1 minus z2 divided by z2 minus z3. Argument of z1 minus z2 divided by z2 minus z3. Now, what does this mean? the amount by which you must rotate the denominator vector so that it coincides with the numerator vector. That's going to be theta, right? Now, z2 minus z3, this is the final position minus initial position. z2 minus z3, therefore, is a vector which is directed like this. Yes or no? This would be the direction of z2 minus z3, right? This is the direction of z2 minus z3, right? z1 minus z2, the direction of z1 minus z2, final position minus initial position. This would be the direction of z1 minus z3 would have this as its direction, right? z1 minus z2 would have this as its direction. Now, this theta is the amount by which you must rotate the denominator vector, which is z2 minus z3, so that it coincides with the numerator vector, which is z1 minus z2. How much is that angle? You have to realize that you have to rotate it clockwise. So this angle would be minus 2 pi by 3. This angle would be minus 2 pi by 3. So this theta would be minus 2 pi by 3. Yes or no? Right? So this theta is minus 2 pi by 3. Right? Which means r is 1, theta is minus 2 pi by 3. So this becomes 1 e power minus I 2 pi by 3 into I. E power minus I 2 pi by 3 is this vector, right? Similarly, you would be able to show, so this turns out to be e power minus I 2 pi by 3. You would exactly in the same way be able to establish that the modulus of this would be 1 and this would be e power I 2 pi by 3. You can check on that. And if you add all of this, hey, this is like 1 plus omega squared. This is omega squared. That's going to be 0. Yes or no? 1. And do you realize this is omega? And this is the conjugate of that. So omega squared, this plus this must be 0. So this turns out to be 0 for an equilateral triangle. So for an equilateral triangle, summation 1 by z1 minus z2 is going to be 0. That means 1 by z1 minus z2 plus 1 by z2 minus z3 plus 1 by z3 minus z1 must be 0 for an equilateral triangle. Right? So this is an important result for an equilateral triangle having vertices z1, z2 and z3. Now, what this would mean is another corollary of this result. See, 1 by z1 minus z2 is like 3 terms. 1 by z1 minus z2 plus 1 by z2 minus z3. Now if I take the LCM and add these, then the numerator of that must be, of this expression must be 0. That's when this will be 0. The numerator of this expression will turn out to be, z1 squared plus z2 squared plus z3 squared minus z1 z2 minus z2 z3 minus z3 z1 equal to 0. So for an equilateral triangle with vertices z1, z2, z3, this must also be true. This must also be true. Right? AM, GM, HM inequality is for non-negative real numbers, right? It's not true for complex numbers. It's true for positive real numbers. AM greater than or equal to GM greater than or equal to HM is true not just for real numbers but for positive real numbers, right? Okay. Now, the converse of this result. That is, if this is 0, implying that this is 0, this equal to 0 would imply this is 0. Is the triangle constituted by vertices, position vectors z1, z2, z3 an equilateral triangle or not? That's the converse of this result. That means given this as 0. That means given this as 0 or this as 0, is the triangle equilateral or not? That needs to be examined, right? Let's do that. Given that this is 0. Now given that this is 0 means this will also be 0. I want to check whether the triangle is equilateral or not. Clear? So there is a triangle. I do not know whether it's equilateral. All that I know is that summation 1 by z1 minus z2 is 0. That is to say that also z1 squared plus z2 squared plus z3 squared minus z1 z2 minus z2 z3 minus z3 z1 is 0. I want to see if this triangle is equilateral or not. Right now, a square plus b square plus c squared minus ab minus bc minus ca can be factorized as a plus b omega plus c omega squared into a plus b omega squared plus c omega. Right? So I could factorize this as this, right? Yes or no? Which means either this is 0 or this is 0. Let me take, for example, this as 0. Let me take this as 0, for example, right? Say z1 plus omega z2 plus omega squared z3 is 0. Which means z1 plus omega z2 omega squared I could have written as minus of 1 plus omega, isn't it? Because 1 plus omega squared is 0, so omega squared could have been written as minus 1 plus omega, z3 as 0, right? Which means z1 minus z3 is omega times z3 minus z2. Yes or no? z3 minus z2 when I transpose it on the other side, right? Now, if I took the modulus of both sides, modulus of omega is 1, modulus of n roots of unity would be 1, mod of omega is 1. So mod of z1 minus z3 is the same as mod omega, which is 1, into mod of z3 minus z2. So one thing for sure, mod of z1 minus z3 on taking the modulus of both sides is mod of omega, which is 1, into mod of z3 minus z2, which is mod of Z3 minus Z2. Now, mod of Z1 minus Z2 is what? Side AB. And mod of Z3 minus Z2 is the side BC. So, for sure, side AB equals side BC. Side AB equals side BC. Oh, Z1 minus Z3. Okay, so sorry, Z1 minus Z3. Okay, so Z1 minus Z3 then realize is this side AC equals BC, right? AC equals BC. This was Z1 minus Z3, not Z1 minus Z2. Right? Yes or no? Now, what is omega? Omega is e power I 2 pi by 3. Omega is e power I 2 pi by 3. What does e power I theta do? When you multiply e power I theta, when you multiply a vector by e power I to I theta, it rotates that vector by theta, right? That means Z3 minus Z2 is multiplied with e power I theta, and it coincides with the vector Z1 minus Z3, right? That means Z3 minus Z2 is this vector. This is Z3 minus Z2. When it is multiplied with this, it becomes aligned with Z1 minus Z3. This is Z1 minus Z3, yes or no? What it says is that when Z3 minus Z2 is rotated by 2 pi by 3, it coincides with Z1 minus Z3. That means this angle must be 2 pi by 3. That means this angle must be 2 pi by 3, yes or no? If you multiply Z3 minus Z2 with e power I theta, the e power I 2 pi by 3, it rotates by 2 pi by 3, and when it rotates by 2 pi by 3, it coincides with Z1 minus Z3. That means this must be 2 pi by 3, right? If this is 2 pi by 3, this is pi by 3, this is 60 degrees. This is an isosceles triangle, this angle equal to this angle. Very clearly then, each of these must be pi by 3 as well. This triangle therefore turns out to be equilateral. This triangle therefore turns out to be. So the converse of the result is also true. Tell me, how was it possible to teach you complex numbers in the beginning of class 11? When people would come up and tell me, first few days in class 11, sir, school mein complex numbers ho gaya. I would feel, how come? How? Why? What did they do? It's just not possible. But all of you have done complex numbers in class 11, right? Have I discussed the condition for 3 points to be collinear? No. No, not all that. Simple terms. Given 3 points with position vectors z1, z2, z3, what would cause the 3 points to be collinear? Okay, even if I have, what's the problem? You have forgotten. That means it's okay to repeat that, right? No issues. We'll even if it is done before, we could have a quick rerun of the same thing. So sorry. This is inertia. So, if there are 3 points, A with position vector z1, B with position vector z2, C with position vector z3, I want to find the condition that these 3 points are collinear. Condition for collinearity of these 3 points. Hey, look at this. If they are collinear, then look at Z3 minus Z1 and Z2 minus Z1. If they are collinear, means Z3 minus Z1 is this vector A to C, and Z2 minus Z1 is this vector, right? Based on their relative orientations, the amount by which you must rotate Z1 minus Z3 minus Z1 so that it coincides with Z2 minus Z1 would be either 0 or pi, based on how they have relatively oriented, how they are relatively oriented, right? So which means the amount by which the denominator vector be rotated so that it coincides with the numerator vector Z2 minus Z1 should be 0 or pi? Yes or no? For them to be collinear? So that means the argument of this is going to be either 0 or pi for them to be collinear. The argument of this is going to be 0 or pi, yes or no? No, it could also be pi. Realize that? Right. Z3, if it was located here, for example, then Z3 minus Z1 and Z2 minus Z1 would have an angle pi. Now, if the argument of a complex number is 0 or pi, that means that complex number, if the argument is 0, it lies on the positive x-axis. If the argument is pi, it lies on the negative x-axis. One way or the other, that complex number is a real number. If a complex number lies on the x-axis, its imaginary part is 0, it must be purely real. Yes or no? So this is a complex number. Its argument is 0 or pi. That means this complex number must be purely real. This complex number must be purely real. That means Z2 minus Z1 divided by Z3 minus Z1 must be purely real. It could be a positive real number or a negative real number, but it's a purely real number. I hope all of you understand this. No, very simple. See, if a complex number lies on the x-axis, these points don't lie on the x-axis. I'm saying this complex number lies on the x-axis. I never said Z1, Z2, Z3 lie on the x-axis. I said this is a complex number, this is a complex number whose argument is 0 or pi. So then this complex number, we call it Z, must lie on the x-axis. Right? And if it lies on the x-axis, it must be a purely real number. Because its y is 0, that means its imaginary part is 0, right? So this is the test for collinearity of 3 points Z1, Z2, Z3. That means all that you need to do is Z2 minus Z1 and Z3 minus Z1. Any one of them could be chosen as Z1, Z2 or Z3, right? So if this ratio turns out to be real, you can conclude that the three complex numbers Z1, Z2, Z3 represent collinear points. Represent collinear points. Points representing Z1, Z2, Z3 must be collinear. Now, suppose there is a point A with position vector Z1. There is a point B with position vector Z2. There is a point C with position vector Z3, and there is a point D with position vector Z4. I want to find the conditions such that AB is perpendicular to CD. Now, take one vector as Z2 minus Z1. The vector AB, for example. Take another vector as, say, Z4 minus Z3. Right? These are two vectors. This is AB and this is CD. The denominator vector is AB, Z2 minus Z1. The numerator vector is CD, which is Z4 minus Z3. Right? Now, the amount by which you must rotate the denominator vector so that it coincides with the numerator vector. This is the numerator vector, this is the denominator vector. Could either be plus 90 or minus 90 depending on their relative orientations. Because see, C for example could have been here, D could have been here. Then it would have been minus 90. Right? That means the amount by which you must rotate the denominator vector so that it coincides with the numerator vector would either be plus 90 or minus 90. That means the argument of this complex number, which is like the amount by which you must rotate the denominator vector so that it coincides with the numerator vector, would be plus minus pi by 2. If the argument of a complex number is plus minus pi by 2, that means it lies on the y-axis. That means it must be purely imaginary. That means this complex number, which is this ratio, must be a purely imaginary number. So which is like Z4 minus Z3 divided by Z2 minus Z1 must be purely imaginary. That means it must be I times a real number. That means it must be I times a purely real number. Yes or no? So this is the, if this happens, then AB will be perpendicular to CD. Right? Suppose there are two segments, A which is Z1, B which is Z2, C which is Z3, D which is Z4. Condition for which AB is parallel to CD. Condition for which AB is parallel to CD. Now again look at this ratio. Z2 minus Z1 and Z4 minus Z3. The amount by which you must rotate the denominator vector so that it coincides with the numerator vector would either be 0 or pi for them to be parallel. Would either be 0 or pi. That means the argument of this is going to be either 0 or pi. For the AB to be parallel to CD, that means this ratio must be a purely real number. That means Z4 minus Z3 purely real. This must be a purely real number. Right? When we are talking of 3 points, we were speaking of collinearity. This time there are 4 points. So we are talking of parallelism. Yes. Y-intercept? Couldn't get you. No, we can work around, but that's going to be a lot more complicated than this. I mean, given 4 points, we can do that. We can define a complex slope. Have I given to you the equation of a line in complex plane? Equation of a circle in complex plane? In any case, we can do that also. Once I give you the equation of a line in a complex plane, if you like, you could do that also. But that will be a lot more cumbersome, right? Now, say Say if I have two fixed points A, which is Z1, and B with position vector Z2. A with position vector Z1, B with position vector Z2. Alright. And there is a moving point P. P is a moving point with position vector Z. There is a locus associated with Z. A and B are two fixed points with position vectors Z1 and Z2. Whereas P is a moving point. Now, if it's a moving point, it has to move subject to a condition, right? Let's say the condition for motion of P is mod Z minus Z1. Z moves in a manner that mod Z minus Z1 plus mod Z minus Z2 is mod Z1 minus Z2. Mod Z minus Z1 plus mod Z minus Z2 is mod Z1 minus Z2, say. We need to figure out the locus of P. We need to work out the locus of P. Okay. Say A is this point with position vector Z1. B is this point with position vector Z2. P, this is the distance between P and A. This statement is like PA. This is the distance between P and B. So this is like PB. This is the distance between A and B. So this is AB. So P is such that PA plus PB is AB. Such is the locus of P. P is such that PA plus PB is AB. Do you realize P could lie anywhere between A and B then? P could lie anywhere between A and B. So the locus of P is the set of points lying between A and B. Because if P lies between A and B, then PA plus PB will turn out to be AB. Yes, you have a question, I'm sure. No? This statement boils down to saying PA, distance between P and A. Mod of this means distance between P and B. Mod of this means distance between A and B. PA plus PB is AB. That means the locus of P is this region. P describes all points between A and B to the inclusion of A and to the inclusion of B, and all points in the meet of the interval from A to B. Yes or no? Suppose I change this. Then what's the locus of P? Yeah, this is like distance between P and A minus PB is AB. Very clearly, P must then lie to the right of B. Then PA minus PB will turn out to be AB. So P will lie on the line joining A and B and to the right of B and to the right of B. So the locus of P is points to the right of B on the line joining A and B. Yes or no? You'll know from in a minute. You'll know that why it will not be an ellipse. I'll tell you that. So far so good, right? Now, okay, let me change this to suit what he's saying. Suppose I said P moves in a manner that this plus this is a constant C, which is bigger than mod Z1 minus Z2, is a constant C bigger than mod Z1 minus Z2. Now check that out. Z is a point such that mod Z minus Z1 plus mod Z minus Z2 equals a constant C, not equal to mod Z1 minus Z2, but bigger than mod Z1 minus Z2. Now realize that this is A, which is Z1. This is B, which is Z2. This length is mod Z1 minus Z2, which is AB. right? This length is AB. And P moves in a manner that PA plus PB. So if P does not lie on AB, then PA plus PB will be bigger than AB, because then PAB must constitute a triangle. Right? So PA plus PB must be bigger than AB. PA plus PB must be bigger than AB. Isn't it? Now if it's a constant C bigger than mod Z1 minus Z2, then PA will constitute a triangle. P will not lie between A and B. Right? And if PA plus PB is a constant bigger than this, then the locus of P will be an ellipse. Locus of P will be an ellipse. Yes or no? P moves in a manner that sum of its distances from two fixed points A and B is a constant. Sum of its distances from two fixed points is a constant, PA plus PB. The locus of P is such that sum of its distances from two fixed points is a constant, C. Locus of P therefore will be an ellipse, whose foci will be A and B. P will describe an ellipse with foci A and B, isn't it? What would be the major axis of the ellipse? C. See that? Right? Because PA plus PB is 2A. Yes or no? PA plus PB is 2A, which is the major axis of the ellipse. So this C will be 2A, the major axis of the ellipse. Yes or no? Right? This C will be 2A, the major axis of the ellipse. What would be the eccentricity of the ellipse? Right, right. Realize the distance between two foci is 2AE. 2AE is this. 2AE is this. Mod Z1 minus Z2. Remember this? This is AE and this is minus AE. 2AE is the distance between the two foci, is mod Z1 minus Z2. 2A is C. 2A is C. So E is mod Z1 minus Z2 by C. That will give me the eccentricity of the ellipse. Yes. Huh? C, given foci, given eccentricity, there can be only one ellipse. Which condition? That means you mean to say a point on the major and minor axis? Those will be limiting points. Sorry? Satisfy that, right? So which will be true? PA plus PB will be bigger than AB. If there is a point on the major axis, the extremity of the major axis would be somewhere here and a point here. Then if P is here, then PA plus PB will obviously be bigger than AB, isn't it? Because this is the definition of the ellipse, PA plus PB. If P moves in a manner such that sum of its distances from two fixed points is a constant, bigger than the separation between the 2 points. That's the basic premise. That's how an ellipse was defined. This is the definition of an ellipse actually. If P moves in a manner, I mean if you fix these points, if you take a pin like this with these two threads, then the segment PA and PB will change, but PA plus PB will be the same. Then it has to describe an ellipse only. Isn't it physically? Is it not? Think of a pin like this and a thread connected to A, another pin at A, a thread connected to B, another pin at B. And if you choose to move P, then sum of the lengths of PA and PB, keeping the threads taut all the time, then PA plus PB will remain constant and the path described by P will then be an ellipse. Actually, I started with my discussion on ellipse with this only. PA. Yes. It will cover exactly all points that satisfy this. In fact, the way we teach you ellipse now is different, but you know, the most ancient understanding of ellipse was this. When they were looking at planetary motion, then PA plus PB equal to constant was planetary motion actually. This is cardinal. You might just want to quickly go back to ellipse and see how favorable it gets. But yes, of course, it is unique if A and B is defined And if this constant C is defined, then there is one and only one ellipse that can happen, and it will cover all points. Trust me. Go back and check your notes on ellipse. Now, and suppose I change this a little bit now. P moves in a manner that this minus this is a constant C, and this is less than, C is less than mod Z1 minus Z2. Then what's the locus of P? A hyperbola. This is like PA minus PB equal to a constant C, which is less than AB, because difference of two sides must be less than the third side in a triangle. So that's why this C has to be. So this is A, which is Z1, which is B, this is B, which is Z2, this is P, which is Z. Then this statement is like PA minus PB, and PA minus PB obviously has to be less than AB, difference of two sides of a triangle has to be less than the third side. In order that PAB constitutes a triangle, PA minus PB has to be less than, so this constant C has to be less than AB. And then this is the definition of a hyperbola. This is the definition of a hyperbola. P then describes a hyperbola whose foci would be A and B. Yes or no? Right?
In the event PA plus PB is equal to C and C is less than 0.
It will be a null set. The locus would be your tummy. It will gurgle around there and make noise. No, just kidding, huh? Now, suppose there is a fixed point A, which is Z1. There is a fixed point B, which is Z2. I want to find the equation of a line in the complex plane passing through two fixed points A and B. A with position vector Z1, B with position vector Z2. I want to find the equation of this line. That means if there is any other point P with position vector Z, then I want to connect Z, Z1 and Z2, which would be the equation of the line in the complex plane. Z is a moving point. That equation must be satisfied for all Z's lying on this line, right? Now, if Z lies on the line joining A and B anywhere, irrespective, then one thing for sure, like we did a little while ago, argument of Z minus Z1 divided by Z2 minus Z1 would either be 0 or pi, depending on the relative orientation of Z, Z1 and Z2. If the argument of a complex number is 0 or pi, then that complex number would be purely real. That means this ratio must be purely real for any Z lying on the line AB on either side, right? That means Z minus Z1 divided by Z2 minus Z1 must be purely real. If a complex number is purely real, see, a real number has a property that it will be equal to its conjugate. Yes or no? 3 equals 3 bar, minus 3 equals minus 3 bar, right? So if z is a, if this is a purely real number, then this will be equal to its conjugate. Yes or no? Can I remove this? So now some algebra here. If this is purely real, that means z minus z1 divided by z2 minus z1 must be equal to its conjugate, must be equal to its conjugate. Conjugate means bar of this whole ratio, that means bar of the numerator divided by bar of the denominator, right? Bar of the ratio would be ratio of the bars, right? So this would be equal to its bar, which is like z minus z1 bar divided by z2 minus z1 bar. Yes or no? Now this is bar of the difference. Bar of the difference is difference of the bars. So remove this. Difference of the bars, right? Bar of the difference is difference of the bars. Remove this. Got me? Yes or no? Let me multiply this out, right? Hash out the algebra, make it a little more graceful than what it is. This is fine. You could leave it at this point. Any z satisfying this condition would lie on the line joining A and B, anywhere, right? But then let's package it a little further, right? So then this is like z into z2 bar minus z1 bar minus z bar into z2 minus z1 plus z1 bar into z2 minus z1 minus z1 into z2 bar minus z1. Equal to 0. No rocket science. Ordinary cross multiplication and consolidation of terms on the same side with z, z bar and the rest segregated, filtered, right? Hey, if I took the conjugate of this number is z1 bar z2 minus z1. This is this number A, right? Say capital A. Now if I took the bar of A bar, then that's going to be the bar of the whole thing. Bar of the product would be product of the bars. So first I'll take z1 bar bar. If you take z1 bar bar, you'll get z1, isn't it? Right? z1 and bar of this, bar of the difference would be difference of the bars. Yes or no? Which gives me this. So this is A minus A bar. That means it's like x plus iy minus x minus iy, which is going to be 2iy, which will be a purely imaginary number. This is A minus A bar. Difference between a number and its conjugate would be purely imaginary, right? So this expression is purely imaginary. Yes or no? This is A bar. A minus A bar is purely imaginary. Clear? So can I just remove this portion? What I do is, I would rather like to convert this purely imaginary into purely real. What would I do? Multiply with I, isn't it? If a purely imaginary number is multiplied with I, it will become purely real. I times t into I would be minus t, which will become purely real. Yes or no? Yes, sir. Let me multiply the whole thing with ni. Right? So if I did that, z minus I, right? This is a minus sign, so this will become minus I. And this purely imaginary will become purely real. Yes or no? No? No, I just multiplied the whole thing with I. See, these two terms I have not tinkered. The minus sign I have just clubbed it with an I. The expression remains the same. And that purely imaginary number was multiplied with I. It will become purely real. Because that purely imaginary number was of the form I times y. If you multiply it with I, then this will become minus y, which will be a purely real number. Right? Are you still lost? And the other two terms are the same. Refer to the previous line. Right? So this must be 0. Right? Now, suppose this is a complex number, because z2 minus z1 is complex, into minus I will be a complex number, right? This is going to be a complex number. Suppose I choose to call this as A. A is minus I into z2 minus z1, where A is complex, right? A is this number. Now, if I took the bar of this, A is a complex number. A is a complex constant. In fact, you want to call it a complex constant because z1, z2 are constants. Minus I is a constant, so you might want to call it a complex constant. This purely real number, this would have been a real constant because this only involves z1 and z2. So this would have been a real constant. This A is a complex constant. Right? So if I took A bar, then bar of minus I would be simply I. Bar of minus I would simply be I into bar of this, which is z2 bar minus z1 bar. Yes or no? Hey, which is this? This is A bar. Right? So this is A bar. A is a complex constant into Z. A Z bar plus a purely real number, a real constant B, equal to 0 is the form of the equation of a line in the complex plane. Yes or no? This turns out to be A bar Z plus A Z bar plus B equal to 0, where A is a complex constant and B is a real constant. So any point lying on the line joining z1, z2 must satisfy this equation. This is the form of the equation of a line. A bar z plus a z bar plus b equal to 0, a being a complex constant, b being a real constant. I'll come back to this with some more facts about, defining complex slopes, etc. But that will be getting further into the details of a line in the complex plane. But let me just give you an overview of some other things before I tell you more about what is meant by a complex plane, a complex slope, etc. of a line described like this. But do you understand the formation of a line in the complex plane? Right? This is the algebraic formation. Clear? Have I told you the equation of a circle in the complex plane? ZZ bar plus, right? I've done that, right? So I don't need to repeat that. Have I told you the condition for a quadrilateral ABCD to be cyclic? No. Hmm? No, but in complex representation. Have I done that? Only you say that. Although, most of the time you will remember what I have done. But no, others seem to be giving me a very blank and dirty look. It's like, kill you. Nevertheless, since, let me give you the benefit of doubt. I'll quickly tell you, what it takes to figure out if a quadrilateral is cyclic or not, right? Say, if this be a quadrilateral, A, B with position vector Z2, have I told you the condition for similarity of two triangles? No. Z3, D, Z4. I want to find the condition for this quadrilateral to be cyclic, right? I want to find the condition for this quadrilateral to be cyclic, ABCD to be a cyclic quadrilateral. All right. Very clearly, this angle, if it is theta, then this angle must also be theta. Yes or no? Right? What is this vector? Z2 minus Z1. Right? This vector AB is final position minus initial position. This vector AC is Z3 minus Z1. Theta is the angle by which you must rotate this so that it coincides with this. Yes or no? Right? So this must be the denominator vector, this must be the numerator vector. So theta is argument of Z3 minus Z1 divided by Z2 minus Z1. Now, the same theta is obtained when you rotate this vector. What is this vector? Z2 minus Z4. And it must coincide with this vector, which is Z3 minus Z4. This vector is Z3 minus Z4. Yes or no? Theta could also have been obtained when you rotate Z2 minus Z4 so that it coincides with Z3 minus Z4. That means Z2 minus Z4 must be the denominator vector, Z3 minus Z4 must be the numerator vector. That means this must be the same as argument of Z3 minus Z4 divided by Z2 minus Z4. Yes or no? Right? If argument A equals argument B, then argument A minus argument B is 0. That means this minus this must be 0. Argument A minus argument B is 0. That means argument of A by B must be 0. Right? Which means argument of A by B means this divided by this must be 0. That means argument of Z3 minus Z1 by Z2 minus Z1 Z2 minus Z4 Z3 minus Z4. This must be 0. Right? If the argument of a complex number is 0, then that complex number must be purely real. Right? That means this ratio must be purely real. That means Z3 minus Z1 into Z2 minus Z4 this must be purely real. If this ratio turns out to be purely real, then the quadrilateral ABCD turns out to be cyclic. Then the quadrilateral turns out to be cyclic. Right? I know you're tired. Some more time. I'm tired too, actually. But one more thing at least let me cover before I discharge you from the clinic. Right. Condition for similarity of two triangles. One more thing that let me mention to you could be useful in terms of figuring out whether this quadrilateral is cyclic or not. Do you know that for a cyclic quadrilateral this property holds good? AC into BD, product of the diagonals, AC into